Okay, I'd like to talk through a little bit how to prove some things about the candy problem, at least a sort of sketch how to prove them. Now, some of this is not stuff I'd expect you guys to be able to do, and some of it is still a little um, sketchy. It's not complete all the way, so it's not stuff that I've even done as completely as it should be done. But I want to, especially if you end up going into math, you'll end up running into places where more and more you're reading proofs that people are doing and you're expected to produce your own. And even if you're not going into math, but going into computer science or engineering or something else, you're expected to be able to read or understand things sort of like this. And so I think it's good for you to be exposed to it, even if it's not exactly the kind of thing you need to do for this class. So one of the things I try to do in this class is expose you to a lot of different proofs. Now, as I said, also, this is probably the last thing I'm going to provide before I come back to class next week. There were some other things I was hoping to get done this week before then, but I think I will not. I think this is all I'm going to do for now. I'm still trying to sort of get some things taken care of here at home before I return, and it's probably important that I leave some time extra for that later on during the week for myself. So this is the last thing we're going to do for this class until next week when I come back. The only thing to do is a week or two after that, so I'll postpone things if I need to. I don't think I will need to, but we'll talk about whatever else. I did already leave you, by the way, a video on relations. It's not for you guys. It was made for somebody else, but I looked it over and I think it's the exact same material as you guys might want to look at. It's what follows the set theory stuff in Unit 2. So take a look at the video on relations. I'll expect you to have looked at that by the time I come back next week. And then take a look at this. All right, so here's the candy problem. You guys are absolutely right. It always ends in a situation where all four people have the same number of pieces of candy as each other. They're all even, and at that point nothing changes because they all gather nothing during the evening up phase, and then they divide their piles in half and pass them to each other, and nothing changes. So and that will always be somewhat less. It will either be it will either be less than the maximum they started with, or if they started with an odd number, it'll be at least less than one more than that. So the interesting thing is how to prove that that always happens. By the way, what I can't do is tell you exactly where it'll end up. There's a lot. I've been thinking about that for a while, and I don't know the answer. I know that if you start with like 22, it'll drop very quickly, and if you start with 20, it actually takes longer to drop. I know that the bigger the separation between the minimum and the maximum, the further it will drop before it settles into a steady state. But what I'm interested in now is in sort of sketching how I would prove that this never actually does anything else than what we talked about. How do you know it ends up settling on one number and for all of them? And how do you know that that number is never bigger than it started with? And so what I'm going to do is use the idea of sandwiching. Well, I'll show you as I go. So the first thing is we would need to, if I were proving this, I'd start by distinguishing between steps and turns. One of the things that's difficult about this is that things take place over time. So you can talk, when I first wrote up proofs for this, I would talk about the minimum number of pieces of candy, and I kept having to say the minimum when. The minimum after one turn, after two turns, or whatever else. And then secondly, as you think about turns, you have to distinguish between what I'm calling turns and steps. So I'm calling the turn the whole turn, which involves an evening up phase, a dividing phase, and a passing phase. And then I'm calling each one of those phases a separate step. So if there were like 16 turns of the game before it settled into a steady state and stopped changing, there would be probably 64 steps, or 48 steps, because there's 3 steps for every turn. So I would probably distinguish between steps and turns. Turn is one full round of evening up, dividing, and passing, and each one of those phases is a single step in the overall turn. Second thing I'd want to do is think about the minimums and the maximums. I'd like to define the maximum as the maximum number of pieces in a game at a certain place, but actually what's really interesting is when that maximum is even, that sort of is a cap on how many pieces anybody can get, but when it's odd, it's not a cap because everybody gets one more to begin with. So I'm going to define M to be the maximum number of pieces over all players at any step in any moment of the game. And I mean not in the middle of passing, but like at the steps. And if M is odd, I'm going to define capital M to be M plus 1. That is the even number that's higher than it. And otherwise, capital M will just be the same as M. So capital M is like my maximum, except that it's one more than the maximum if there's an odd number. And then my first claim is that nobody in the game will ever get more than capital M pieces. That will never be crossed. And there's basically, the reason is because there's only 2 ways you can gain pieces from what you can gain, you can increase in the number of pieces you have. One is if you have an odd number and you pick one more up from the bank, so to speak, in the middle of the table. And in that case, You can't get over M because M was already one more than the maximum number in the game anyway. So that won't get you above M, capital M. The other way you can get more pieces than you had before is if you pass half to your left and pick up half from the person on your right, and the person on your right has more than you do. In that case, as you pass, you're going to be getting more than you passed. But in that case, the person on the right had more than you do, so you already didn't have the maximum. So you have to look, and you're going to have still less than he did because you got half of his pile, but you passed off. You only had, after you passed, half of what you used to have, which was smaller than that. So I've written that out here. There's only two ways to gain pieces during a step. One is by adding one to an odd amount, which cannot result in something greater than M. The other is by passing from player P to player Q, where player P used to have more than Q, but that means Q's new value must be less than P's old value. And then in a indented portion, I wrote how you'd actually write that out if you're trying to prove it more formally. You'd say, you give them numbers, letters. You'd say, well, let X be the amount P used to have, let Y be the amount Q used to have. After the pass, Q has X plus Y divided by 2 pieces. He has half of his pieces plus half of P's pieces. So you know that Y is less than or equal to X because we're assuming that the player to the left, to the right had more than us, which is less than or equal to M because M is bigger than at least as big as everybody at the table. So X plus Y over 2 has to be less than X, less than or equal to X, which has to be less than or equal to M. So my new value has to be less than or equal to M. So that's all a way of saying that nobody, if you start with, say, 19 pieces as the maximum, nobody can ever get more than 20 through the entire rest of the game, is what that's saying. So there's a cap on how big things can be. That already tells you that this can't keep growing infinitely. You can't keep collecting things from the middle in a way that keeps growing infinitely because nobody ever gets bigger than that 20. All right, the next thing is to look at the minimum number of pieces and show that people can't ever get smaller either. So let min, I can't use M already because I did that, let min be the minimum number of pieces in the game at a certain moment. And my claim is that as long as somebody has min, as long as the min is a certain value during the game, no player can ever be fewer than that afterwards. So if at some point in the game someone has 5, from there on out everybody has at least 5. If some point in the game somebody has, if the 5 is the minimum. If some point in the game the smallest number of pieces is 10, from then on everybody will always have at least 10. And the proof is similar. There's only one way, it says to gain pieces. It should say there's only one way to lose pieces during a step, which is by somebody passing you less than you pass on. But in that case, you have more at least than they had, and they already had the minimum. So it's similar to the first one. Now, the key to this whole thing is that I'm going to look at the gap between the minimum and the maximum. I'm going to say, look, the capital M maximum is like the highest we have in the thing, like 20, suppose, and the small min is the lowest we have. Let's call the gap between them delta. I could have picked anything I wanted here. So I'm defining delta to be the gap between M minus min at some point in the game. Delta, again, has different values as the game progresses. So if we start with 20, 10, 8, and 7, 20 minus 7 is 13, so the gap between the maximum and the minimum is 13. If we started with 19, 10, 8, and 7, it would still be 13 because we wouldn't go 19 minus 7. We'd add 1 to 19, make it 20, and go 20 minus 7 because capital M is the even number. Okay, so the delta is the gap between the 19 and the 7. What I'm going to show is that that never gets any smaller. It always decreases or at least or maybe sometimes stays the same. So my first claim is that it's non-increasing as the game non-increasing as the game progresses. It always gets squeezed. What I'm going to show is that the difference between the high and the low continually gets squeezed smaller and smaller and smaller, and that's how we know that eventually everything ends up the same as each other. So my proof for that is really simple, that is non-increasing. I know it can't increase because the maximum never increases and the minimum never decreases, and so they can never get farther apart from each other than they are at a certain moment. Okay. Then the next claim is really important. Let player P have P pieces, which is greater than the minimum. Then after the next step, it still has to be greater than that original minimum. So if I look at the game at a certain point in time and the minimum number of pieces is 6, and somebody else has more than 6 pieces, they can never fall after that down to 6. They can never get as small as 6. So once something moves away from the minimum, it can never fall back to it. That's really important. Again, the idea is exactly the same as before. The only way you can decrease in pieces is to be past fewer than you pass on. But in that case, you'll still have more than the person to your right had, and he already had the minimum. So you'll still have more than the minimum. So no matter what, once you crossed above a minimum, you'll never fall back to that minimum. Now, the min itself might increase like you might have 8 and the smallest value is 6, and then later on as the game progresses, the person with 6 might grow to also have 8, and now you suddenly have the minimum, the new minimum, but you'll never fall back to the old minimum. Okay, and then this is the trickiest step of the whole thing. This is why it's not easy to prove by itself. What happens is sometimes the minimum doesn't grow. But what happens is that there's a whole bunch of people who have the minimum and one of them grows. So here's the definition. I'm going to use Z. I don't know why Z. I could have probably picked a better definition. Mathematicians tend to use just single letters, and probably I like the computer science approach to things here. I probably should be using variables that have meaning to them. But anyway, let Z be the number of people with the minimum pieces of candy at a particular point in the game. So I'm looking at the game at some place, or whatever we call this. I'm calling it a game, and we have 20, 10, 8, and 8. Then there's 2 people with a minimum. So Z is 2. Or if there's 27, 7, and 7, there's 3 people with a minimum, so Z is 3. Or there's 20, 10, 8, and 5, there's only 1 person with a minimum, so minimum is 1. Now, if all are the same, 10, 10, 10, and 10, then there's 4 people with a minimum, so the minimum is 4. The number of people with a minimum is 4. So Z is a number either 1, 2, 3, or 4. So here's my claim. Each step, either Z decreases or delta decreases, and the next step means each step. That should be gone. Each step either Z decreases or delta decreases or all the players are already equal. So 3 things could happen. First of all, I have something like 10, 10, 10, and 10, and then nothing changes at all. Delta doesn't decrease, Z doesn't decrease, and everybody's equal. But if there's a difference between the pieces at all, then either Z gets smaller or delta gets smaller. Maybe not both. So here's the way that we'll prove that. Assume the player is not equal in pieces, because if they are, then it's already done. If they're not equal in pieces, then we know Z is less than 4, because they're not all 4 the same. And we know that that means that there has to be somebody who has more pieces than the minimum. And that means there has to be some player with the minimum number of pieces whose right-hand neighbor is that guy. So there's at least one person with a minimum number of pieces whose right-hand neighbor has more pieces than him. At the next step, that person will no longer be at the min, because he'll get more pieces than he gives away. And since he will grow, and since none of the other people who didn't have the min can drop back to the min, because we had that from before, the number of people with a minimum number, Z, has to decrease. So that's one way it could go. The other way it could go is that the min itself could rise. Like somebody could be at 5 and that could be the min, but they could actually now get 6, and now the whole min could change to 6. And now you could suddenly, as that minimum person moves up, you could now suddenly have a whole bunch of people who have the minimum again. But not because they become smaller, but because the whole minimum has moved up. But in that case, the minimum itself has increased. So the point is that each step, either Z decreases, less people have the minimum, or delta decreases, the minimum moves closer to the top, or all players are equal in pieces. Right? And now I'm just going to do a little algebraic trick to prove what I need. The point is, though, if you think about it, that the way this works is every step, one of the minimum players grows, gets more than the minimum. And another one, the next step, gets more than the minimum. Eventually, the last player with the minimum gets more than the minimum, and suddenly the minimum has moved higher. And so that gap between the max and the min has grown smaller. And then the whole thing starts again. After at most 4 steps, the minimum will grow 1 more at least. And now we have the gap between the minimum and the maximum still smaller. And since it keeps getting squeezed, sooner or later it has to all come together. And and that's basically what we're doing. So the way I'm going to do that is create a formula. I'll just say let S be delta times 4 plus Z. I'm saying that it takes at least 4 steps to decrease delta. So I'll just count every delta as worth 4 Z's in a sense. So let S equal delta times 4 plus Z at any point in the game. Now I can prove that either everybody has an equal number of pieces or that increases. And it's because Z is less than 4. So if Z decreases, then and delta stays the same, then it decreases. But if delta decreases, then even if Z can be at most 4, so it can increase by most 3, and since delta decreased, S still has to decrease altogether. So that proves that S keeps decreasing, and now I can simply claim that means we eventually reach a place in which all players have the same number of pieces, and the reason is because S keeps decreasing and it's finite, and it decreases every turn, so eventually it drops down to 0. And, or maybe that's... maybe to 4. I have to think about how that works actually. Eventually it drops to the place where all the players are equal, because then delta stops decreasing after that. So that means eventually everybody has the same number of pieces. Now I just have two more little things to say. One is that if everybody has the same number of pieces and it's even, then the game's in a steady state, meaning nothing changes. And it's obvious because every player does exactly the same thing. They receive nothing, they pass the exact same amount as they receive, and they end up with the same things as before. And then I just have to quickly deal with a special case where they all have the same thing, but it's odd, like they might start that way with 5, 5, 5, and 5. In that case, it's a steady state of 6. So in that case, what happens is on the very next turn that makes it even, and then it immediately falls into we can apply the claim just above it. So that means that all the players end up with the same amount, which will be some even number, which is less than or equal the capital M we started with. All right, now to be really careful with all these proofs, to make them really formal, you'd have to deal with the fact that the mins and the deltas and the z's and the s's keep changing over time. They're really functions based on the number of steps. So what I would actually do was I would define every one of these things with a subscript. I would have defined min as min sub I, and I would have said that's the minimum after I turns, and max as max sub I, and that's the maximum after I turns. And then my theorems would say something like min sub I is always greater than or equal to min sub j if I is less than j. If I is greater than j, that would be a way of saying the minimum never goes down over time. Things like that. And that's the way you'd actually do this absolutely formally. But this is pretty formal as it is. So I don't know if that seems hopelessly too complicated for you. What I want to show you is that you can actually work this out so that everything's pretty well specified, and with a little more work we can make it absolutely formal. But most of it is based on key ideas that you probably already saw. So if you were reading this in a journal, you wouldn't memorize every step of this, you'd sort of check it. What you'd want to get is that basic idea, which is that the mins never go down and the maxes never go up, and the number of people at the minimum keeps decreasing, and every time it decreases to 0, it means you move the minimum up 1, so that the gap between the two keeps squeezing closer and closer, and that proves that eventually you have no gap between the players, and there you get a steady state. And then you just need to realize this steady state stays as it is, whether it starts even or starts odd and it moves 1 up to even and then stays there. All right, so I just wanted to sort of show you some of the mathematical things you would do in trying to prove something like this. I don't know, as I said, actually how to find out exactly where you're going to end up. If you gave me a beginning set of numbers, I don't know any way better than just trying it to see where you end up. Although I've played around with that a little bit. I've discovered some things. The gap between things is very important, and so is the positioning of them. Like if you start with 22, 22, you immediately drop to 11, I think. But if you start with 20, 22, 2, you do much better than that. I guess after 20, 22, 2, you end up with 20, 11, 2, 11. And that leads you with, and then that becomes 20, 12, 2, 12. And then you end up with 16, 8, 8, 16. And then that actually leads you to 16, 12, 8, 12. If I did that, no, 16, 12, 8, 12, which I think then leads you to 14, 10, 10, 14, and then 14, 12, 10, 12, and then 11, 11, 11, 13, 11, 11, 13, which becomes 14, 12, 12, 14, which becomes 13, 14, 13, 13, 14, or something like that. Eventually all becomes 14s, I think. I may not have done that quite right. Anyway, so there you are. I will see you all in about a week. I wanted to at least give you something more to think about. Let me say one more thing. Hold on. Let me say one more set of things. I completely forgot this, but let me put it in right here. If you go look at the first homework assignment, there's some stuff you might want to be thinking about right away, and I'll show it to you right away. I forgot I hadn't done this, so let me just talk through this right now before I finish. There are, in this homework assignment, which is not due until at least a week after you come back, and maybe much later, the homework assignments are set up strangely. What I do is I give you a whole bunch of problems, tell you the number of points that each one is worth, and then you do as many as you want to get 10 points worth. Now, you're allowed to do more than 10 points worth, so that if you miss some points, you can still get 10. In other words, if you do exactly 10 points worth, you have to ace them to get all 10 points. If you do like 20 points worth and you miss half of them, you'll still get 10 points worth. So it's up to you how much you want to pad your score to cover for things you don't get right by doing more problems. So that's the way it's going to be work every time. So here's the problems that are sitting here. You can see what they are. The 3 I want to talk about are the 3 that are here at the beginning. Let me see if I can shrink this a little bit. They're similar to the candy problem. So let me make sure they make sense. What I want you to do is do as much as you can to solve the problem. Like the candy problem, it's not clear what a full solution would be, and I'll give you 5 points if you get really a long way, and fewer points if you get less. So let me talk about each problem. The first one's called the egg problem, or I'm calling it the egg problem. You're going to drop eggs out of the windows of a building onto a soft surface, like a big bunch of mattresses or something. The building has 50 stories. You want to find out what's the highest story from which you can drop an egg without it breaking. You don't know. But you're given 2 eggs, and those are all you have, and they're equally fragile. You want to try as few trial drops as possible. So one way to do this is start with a 1-story drop, and if it doesn't break, you move up. 2-story drop, if it doesn't break, you move up. 3-story drop, if it doesn't break, you move up. If it breaks at, say, number 20, then you know 19 is the longest you can drop from. The problem is, you ought to be able to do better than that. So another way you could do this is drop like right away at 25 stories and see if it breaks. And if it doesn't, you've eliminated the bottom 25. You can just check the last 25. The problem is if it does, you're now only to 1 egg, so you can't cut it in half again. Now you have to start at floor 1, because if you drop the second egg at floor 12 and it still breaks, now you have no way to know which of the bottom 11 ones was safe. So once you get down to 1 egg, you sort of can't do it. You can kind of do a binary search, except only with the first egg, because as soon as it breaks, you're down to a single egg, and then that single egg you have to sort of do a linear search in. So the question is, what's the way to find out the answer to this in the minimum number of drops? If you really want to do a more thorough job, try to figure out what a formula is for this for n stories, not just 50. But for now, just finding out how to do it with 50 stories is good. So figure out the best you can do it with. You can post even what number you got, and I'd be glad to tell you whether I can beat it or not. But that's something to think about. The second one is an elimination problem. You might be able to find this if you look it up online. Please don't go look it up online to find the answer. Just try to figure it out yourself. You have 8 people, for example, in my example, arranged in a circle, and you do this eeny, meeny, miny, mo thing, where you start from person 1 and count around and eliminate every second person. 1, 2, 3, 4, 5, 6, 7, 8, and you eliminate 2, 4, 6, and 8. And then you keep going. You have 1, 3, 5, 7 left, 1, 3, 5, 7, and you eliminate 3 and 7, and you've got 1 and 5 left, 1, 5, and the last person left is person 1. So you just keep counting around 1, 2, 1, 2. Every time you eliminate somebody, they drop out of the circle, and you keep going. And in this case, 1 ends up being the person who lasts the most. If you start with 9 people, who ends up being left at the end? That's a good question. 10 people. So that's my question. If you have n people, can you find a quick way to discover who will be left? If you were playing a game and you were doing this game and they told you there's going to be 25 people, could you rapidly figure out the perfect position to be standing in so that you could win the game by lasting longer than anybody else? There is a pattern to this, so it's worth looking for and trying to, if you can, explain why the pattern works. And the final thing is called the MU problem. So this is related to formal grammars that we're going to do near the end of the semester. But start with the string MI. You have strings of letters, and you have 4 rules, which are called production rules, that you can use to change the string. So you start with MI as your starting piece, and you can do whatever you want of the following 4 things over and over until you are finished, which is whenever you want to finish. So one thing you can do, rule A, is you can add a U to the end of any string ending in I. So MI ends in I, so you can make it MIU. If it was something much more complicated, as long as it ended in I, you could always add a U at the end if you wanted. The second thing you're allowed to do, step B, is to double the string after M. So if you had MIU, you could make it MIUIU, or anything else like that. If there's more than one M, you can double the string after any one of the M's. Replace any III with a U. For example, if you had MIIIU, you can replace it with MUU. So any 3 I's you can replace with a U if you'd like. Or fourth, if you have 2 U's, you can cancel them out. So if you had MUUIU, you could just reduce them both to just get an MIU. So the question is, how can you get to the string MU? So either find a way to do it, show me how to get there, or show me good reasons to think that you can't. And so those are 3 questions. Now what I'm asking you to do is just as many problems as you can get 10 points for. So you could do 2 of these and solve the whole do the whole homework, or you could do just 1 of these and then do some other points, or you could even just do all the other stuff. So the other things is there's a series of proofs. Now we haven't talked about proofs yet, but we will soon after I get back. So you can read A3 if you'd like, or you can wait till I get back to look at proofs. Those will be 3 points each for a successful proof, 1 point for a counterexample. We're going to have some other problems. There's only 2 of them, and they're only a point each. We have not talked about Chapter 10 yet, and we will when I get back. Again, I'll probably delay that first due date, so don't sweat it too much. And finally, there's a couple things you could write programming problems for if you'd like. And so feel free. Those would be worth 3 points each. Okay, that is all that I have to say. Now we'll call it a day.